have to do with electrochemistry, or what we call redox reactions. Electrochemical cells is an apparatus that allows redox reactions to occur by transferring electrons through an external current connector. Batteries are an example. There are two types of electrochemical cells. One's called an electrolytic cell, which are those in which electrical energy from an external source causes non-spontaneous chemical reactions to occur, and voltaic cells, which are those in which spontaneous chemical reactions occur to produce electricity and supply it to an external circuit. Oxidation reduction reactions, there's a direct redox reaction where you have an oxidizing and reducing agents in direct contact. For example, copper mixed with a solution of silver will produce copper ions and silver as a solid. Electrodes in cells are where surfaces upon which oxidation and reduction half reactions occur. The cathode is the electrode at which a reduction occurs, and an anode is the electrode at which oxidation occurs. Remember that voltaic cells are those in which spontaneous chemical reactions produce electricity and supply it to an external circuit. Example would be a battery. A battery is an example of a place where spontaneous chemical reactions producing electricity by supplying it with electrons. Here's down below is an animation of what happens in a battery, where it gets electricity from the electrons in the chemical reaction inside the battery. In order to construct a voltaic cell, you need to provide it with two half reactions that are contained in two separate vessels. Each vessel and its contents are referred to as half cells. So, in the case here, you have one vessel. This is the site of reduction, and then you have another vessel here with the site of oxidation. The anode, again, is the place where oxidation occurs. The cathode is the site where reduction occurs. Electrons always move through a wire from the anode to a cathode. Anions, which are negative, always move toward the anode. And the way I remember this is they look the same. Okay? The reason being is because the anode has a positive charge, and they always move through what we call a salt bridge. Cathodes, cations, which are positive, move to the cathode because, again, the cathode is negative in charge, and the opposites attract, and they move through a salt bridge. Under standard conditions, the voltage is commonly referred to as the standard cell potential. Standard conditions of a cell is 25 degrees Celsius, 1 atmosphere pressure, and 1 mole solutions. You'll be given a chart to figure out these standard cell potentials. So don't worry about that now. So in the case of a simple reaction, there is an electric current, but in this case, the electric current is going to be trapped. So we know that this will cause a redox reaction. When we take some zinc metal and put it in copper ions, we'll get some copper plating here. This is because zinc is being oxidized and the copper ions are being reduced to become copper solid, and then zinc would become zinc ions in solution. Okay, so over time this blue is going to probably turn more clear. Okay, so here are half reactions. Again, zinc is being oxidized and is a reducing agent. It's giving off 2 electrons. The copper solution is being reduced and is the oxidizing agent. And here's the half reaction where it's accepting 2 electrons. Now, this movement of electrons is not being trapped in this case, so therefore no voltage is being measured in this example. However, we take a look at what's happening here. The electrons are being transferred from zinc to copper 2, but there is no useful electric current. Even though you do get a redox reaction, this movement of these two electrons is not being utilized. Okay? So, when we separate them, however, this is when we can actually get an electric current. Okay? So, to obtain a useful current, we separate the oxidizing and reducing agents, so the electron transfer occurs through an external wire. Here's our wire. Okay? This is accomplished in what we call a voltaic cell. Okay? And this is just like a battery. So again, electrons travel through an external wire creating voltage, and up here you have a voltmeter, which is measuring the flow of electrons. You have a salt bridge, which is located down below, which allows the anions and cations to move between compartments. Anions always move toward the anode through the salt bridge, and cations always move towards the cathode through the salt bridge. The salt bridge maintains electrical neutrality and completes the circuit by allowing anions and cations to pass through it. Without the salt bridge, you would have a short circuit and the electrons will not be able to move freely. Electrons are then replenished through redox reactions, and the battery dies when all the anions and cations are used up on both sides of the salt bridge and the salt bridge has run dry. Okay? So once these cations start running out, and which is being replenished by this salt bridge, which has salt in it, then the battery actually dies and it doesn't work any longer. Okay, here's another example. This is telling us that the movement of cations is always toward the cathode and the movement of anions is always toward the anode. The electrons always move from anode to cathode. Alright, now why? The reason being is because electrons are driven by those electromotive forces. Okay, so in other words, the reducing agents and the oxidizing agents are coming into play here. Okay, the anode is the source of electrons, and the cathode is the sink for electrons, where they actually are stored. Okay, anode is the site where they come from. The sink is where they go. In this case, we have a zinc-copper voltaic cell, where zinc's the anode, copper is the cathode. And we indicate that we're actually getting a 1.10 volts for this reaction. In other words, that is how much movement we're getting from these electrons, which are powering this this battery in this sense. The more positive the standard potential is for a half reaction, the greater the tendency for the reaction to occur as written. Therefore, the half reactions with the most positive reduction potentials are the most powerful oxidizing agent, while the half reactions with the most negative potentials are the most powerful reducing agents. Again, you will get a list, and the list on there will tell you the strongest oxidizing and reducing agents. In order to figure out the cell potential, here's a simple formula. So the cell potential is the standard potential at the cathode subtracted from the standard potential of the anode. Okay, so for example, if we have a cathode where we have copper, which is being oxidized to copper 2+, on the list it'll tell us 0.34 volts. And at the anode, we have negative 0.76 volts. When we take a look here, we look up these standard reduction potentials, and we subtract these two numbers from each other. we get a total voltage of 1.1 volts, okay, which is the potential energy driven by the movement of these electrons. So the overall reaction here is written as follows, where we have our standard electrical potential of 1.1 volts. The sign of the potential cell tells you the direction of the electron flow. A positive value means the reaction will occur naturally in the direction written, so then therefore the voltaic cell will work. And a negative value means the reaction will not occur naturally in the direction written, so therefore the voltaic cell will not work. Okay, so take a look here. What you're going to be doing here is you're going to be comparing, and again you want to take a look at which one is the best reducing agent and which one's the best oxidizing agent. The further to the top of the list is the better oxidizing agent, and the further down, the further up on the list is the better reducing agent. The further down is the better oxidizing agent. So in this case, since Fe is higher on the list, it's the better reducing agent, and cadmium is a better oxidizing agent because it's lower down. So when we take a look here, we know that Fe, since it's higher on the list, will be a better anode than cadmium. And cadmium 2+ is a better oxidizing agent, so therefore that's going to be our cathode. Okay? So this is how we write it. Our cathode is over here, our anode's over there. It doesn't really matter as long as you correctly label them. So the overall reaction here is we have Fe plus Cd2+ goes to Cd plus Fe2+, and when we subtract our standard potentials, in other words, we take our energy from our cathode, subtract it from energy from our anode, we get 0.04 volts, which is not very much at all. And again, the flow of electrons always goes from anode to cathode. But our cations always flow from anode to cathode as well. Okay, so they're always attracted to the cathode. Electrolysis is another type of electrochemical reaction where you're dealing with electrolytic cells, in which electric energy from an external source causes non-spontaneous chemical reactions to occur. An electrochemical reaction is a non-spontaneous reaction, but can be driven if you apply some external electrical energy. Electrolytic cell has a battery that gives the energy